All right, welcome to another exciting episode of today's AP Chemistry here at Spain Park. Today is April the 21st, Friday. Oh, say, congratulations. Now, I was keeping track. Now, I sent you a just congratulations, but it said that only goes to your email, which apparently you didn't check. But anyway, congratulations. And so, how did it go in the first with the singles?
I lost against Finley, 3-6, 4-6.
Oh, so it was close.
It was good, and then I won in a tiebreaker.
Yeah, Coach Gaines kind of gave me the rundown on the second set and tiebreaker.
It was 6-3, 4-6, and then the tiebreaker was 10-8.
Yeah, but it was 4-6 is a little bit misleading as far as the beginning of the set.
2-5.
Yeah.
And then, it was scary.
Yeah. All right. Anyway, congratulations. I know that's huge, and so that's a big win. Okay, go Jags. All right. So, if you note up here on the screen, okay? No, stay there.
Zooming it in.
If you look up here on the screen, you'll see that my battery that we created yesterday still has a voltage. Okay? Still has a voltage. So, we can look and just go, and the electrons are flowing. And as long as we have electrons available in our solution and in our metals, then we're going to have voltage in our battery. Today we want to talk about how to really construct a battery, what's the electron flow going to be in that battery, all the different parts of the battery, and just kind of go from there. And then what happens if we're not at standard conditions. Unfortunately, I'm not going to be able to get to the back half of the chapter today, which means I'm going to have to take Monday, part of Monday for sure, to talk about electrolysis so you can at least have a chance at answering those questions. And then that will conclude our content for the year, okay? Leaving us 4 short days to review. Now, are any of you in any of the AP English classes, are you going to the AP Palooza tomorrow for that? Okay, no, it's only the teachers that are kind of in this program. I think mainly it might be the junior teachers, okay, the AP Palooza. Because if you happen to be going to AP Palooza for English, I will be presenting the chemistry sessions at that AP Palooza at Hewitt Trustful. So you are allowed and encouraged to come to that if you want to come to the chemistry session as well as your English session. There will be 3 different sessions. I recommend if you're coming to the chemistry session, you come to session 2, which will be the 3rd session of the day, the last session of the day. The problem is that I can't give you bonus when other people don't have the same opportunity. If everybody was allowed to go, I would give you bonus. It'll mean a lot to me if you come, but I can't give an unfair bonus out that's not equal to everyone. Okay, and what I really wish I could do is give you grade bumps based upon how you do on the AP exam itself. For instance, if you somehow were making a B in the class, but you made a 4 or 5 on the AP exam, I want to be able to bump your grade to an A. If you were making say a B in the class and you made a 1 on the exam, I kind of want to bump you down to a C. but I'm not allowed to do that, and so but that's the way I would like to do it, because everybody should be able to do better, at least a 2. Okay, so here we have this. Now, let's look at and construct our own cell. So if we look over here, okay, if I have a piece of copper solid in a solution of copper sulfate, and I have zinc sulfate with a piece of zinc metal in this beaker of zinc sulfate, and both of these are at 1 molar because that's standard conditions. 1 molar and, well, I'm not going to put that there, that's going to be in the way. 1 molar and 1 molar. Standard conditions, whenever we see the little degree symbol, so we add to it for thermochemistry, is always 25 degrees Celsius, 1 atmosphere. For gases, it's 0 degrees Celsius, 1 atmosphere. For electrolysis, it's still 25 degrees, 1 atmosphere, but all of my solutions need to be 1 molar. That's just when we say standard conditions, all those are assumptions to be made about standard conditions. So I have this, and if I go on page 1105 in the textbook, and you look up the reduction potential, this is the values that are in the back of the book. Now these values are always given to you. So from yesterday, if I know these values, which one of these substances is going to be oxidized, which one's going to be reduced that we know?
Copper.
Copper. How do you know, Jace?
It's the larger, it's positive.
It's the more positive value. It's the bigger number. Now, both of these could be positive, both could be negative. It's always the more positive value is going to be the one that gets reduced. Okay? So that means the copper is getting reduced, which means, what does reduction mean? Gains electrons. So if the copper is getting reduced, what does that mean is happening to the zinc? It's being oxidized, because in every reaction, in a redox reaction, it's not redox, it's not ox, it's redox. One thing is reduced, one thing is oxidized. If something loses electrons, something else has to gain the electrons. It's got to always work that way. And so if the copper is being reduced, that means the zinc is being oxidized. What does that mean about the direction of this reaction? It goes the other way. So the zinc is going from zinc metal to zinc 2+ ion. So when I come here in my cell, first off, why is my voltage still rating 0 even though I have everything set up? Circuits open. Oh, so close. Oh, right there. Okay. The circuit is open. Well, how do we close it?
You gotta put something that can conduct electrons back and forth.
What do we call that something? A salt bridge. Y'all, quit being so mean. This is my salt bridge. Okay? Now, y'all, you need to define this. This is important. Write this down. The salt bridge. Dash. Allows the flow of ions to maintain electrical neutrality. So allows the flow of ions to maintain electrical neutrality between the cells. Now, most of the time, gentlemen, we need to really focus. Most of the time, the salt bridge contains potassium nitrate. That just seems to be the drug of choice, chemical of choice. Potassium nitrate, okay? It's not anywhere in the reaction. It's not part of it. They're spectator ions, but they're just going to flow to maintain electrical neutrality. Now, when we put the salt bridge in, now we're going to get some kind of voltage. And again, this is deep. What does a voltmeter measure? Volts. It doesn't supply power to the system at all. It just measures the voltage to a battery. Okay? Now, so in this now, let's talk about what's actually happening. So if our balanced equation is going to be Cu2 plus aqueous plus zinc solid is going to go to what? Cu solid plus Zn2 plus aqueous. Once again, no charge, no points. You're going from a solid to an ion to a solid. Ions are charged particles. It's not going from zinc to zinc. It's going from zinc to zinc 2 plus. Okay? Now, so what's happening then in, where's red? Where's red? Where's red? What happened to red? Oh well, we'll go green. What's happening to the copper? Okay, but it's gaining electrons, so how's it changing? It's being reduced. Okay, I have it right here. It's being reduced. I forgot to erase that part. This one's being oxidized. So what's happening in this cell? So the Cu2 plus is being changed to, where do you think that's taking place? On the copper electrode itself. This is where the electrons are going to be. So the copper is precipitating onto this, getting the electrons. This is the reduction cell. It's being reduced. So what's happening here on this side?
It's losing the solid. It's
Okay, so this is changing into that. Zinc metal is being changed, it's losing, it's being oxidized and forming Zn2+. So this is oxidation. Now, very important, the anode and cathode are defined by that process. The oxidation always occurs at the anode. Reduction always occurs at the cathode. Anode and cathode. So let's talk about electrons. Where are the electrons that this copper is getting coming from? No, they're not coming through the salt bridge. They're coming from this zinc, right? The zinc metal here is losing the electrons. Well, those electrons are here, and they're traveling through the wire into here. So this is becoming electron rich, negatively charged. This is becoming electron deficient, positively charged. Now this is kind of confusing. I don't like the way that they name things, but anions are negative. They're called anions because they collect at the anode. So what does that make the charge of the anode? If negative is attracted to it, what's the charge? Positive. The anode is positively charged. Cations are attracted to the cathode. Cations are positive, therefore your cathode is negative. Now, it's negative because that's where the electrons are all coming. There's electron rich right here. So the electrons are flowing through the wire because, remember, metallic bonding, a C, a free-floating valence electrons. Electricity is the flow of charged particles. In a wire, it's the electrons flowing. But as the copper precipitates out, first off, what's happening to the mass of that electrode? What's happening to the mass of the piece of copper down in there? It's increasing because copper that's in the solution is precipitating onto it. Mass isn't, it's not changing, it's just this is increasing, the mass of the copper in the solution is decreasing. But what's happening to my charge then? If positive's leaving, it's becoming very negative. So without the salt bridge, immediately this becomes negative and it resists the flow of electrons coming in because now everything's negative and they just begin repelling, so everything stops. So we really don't get any flow without the salt bridge. So the salt bridge, the K pluses have to replace the Cu2 pluses, has to maintain electrical neutrality. So the K pluses are going to flow into this here. So we're going to end up getting some K pluses. As this leaves, K plus is going to replace it. For every copper that leaves, I need 2 K pluses to come in. I have to maintain electrical neutrality. Now on the other side over here, what's happening? The opposite. What does that mean? The zinc is coming in, so what's happening to the positive charge in my solution? It's going up. Okay, it's going up. So what has to happen? The negative nitrates have to flow in to balance it out, to maintain electrical neutrality. The function of the salt bridge is to allow the flow of ions to maintain electrical neutrality. Okay? So, follow the negative. The negative's all going to go the same direction when we're trying to decide on the salt bridge and all that. Electrons are always going to flow from the anode. That's what's losing the electrodes. They flow from the anode to the cathode. Electrons travel through the wire, but ions travel through the solution. Electricity is the flow of charged particles. In metals, the charged particles are electrons. In solutions, the charged particles are ions. So in the metal, the electrons are flowing. In the solution, the ions, but it's negative. Electrons are negative, 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 negative. Nitrates, negative, 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 going this way. The positive is always going to go the opposite direction of the negative. So the positive is coming that way. Got that? All right. Now, the last thing we do is we calculate E cell. What's the simple equation?
E red minus E ox.
E red minus E ox. Okay, so it's going to equal 0.337 minus negative 0.763, which is going to equal 1.10 volts. We don't have to worry about multiplying by any coefficients. We don't have to do anything. It's just E red minus E ox. All right, so there's a lot of takeaways from this, okay? I'm gonna let you finish copying that down, and then we're gonna just summarize everything we just did. And I'm gonna point out the things you must know. First thing we know, when you're given the E cells, the more positive value is the thing being reduced, the other one is being oxidized. Values are always given as reduction potentials. So the thing that's being oxidized is going to go in the opposite direction than what it's written in the book. That's the first thing you need to know. You already wrote that down, okay? The more positive value is the thing that's going to get reduced. The other thing get oxidized is going to go in the opposite direction. If we needed the sign, the oxidation potential of this is positive 0.763. But we don't worry about that. We always just plug it in to here. So the second thing is the easy calculate the E cell. It's just E red minus E ox. Don't try and change signs. This negative sign changes the sign for you. Just put in whatever value is given is a reduction. Put that in, E red minus E ox. Okay? Third thing, reduction always takes place at the cathode. The cathode is defined by the electrode where reduction is taking place. Oxidation always occurs at the anode. Vowels stay together, consonants stay together. Cathode reduction, anode oxidation. A and O, C and R. All right, you got a 50-50 chance on that one. Just keep the vowels together, consonants together. The electrons will flow from the anode to the cathode. Now, the way I keep that straight is I know the anode is oxidation. That's where I'm losing electrons. That's the source. You're losing those 2 electrons. The electrons are being given to the thing being reduced. So they're going to flow from the thing losing to the thing gaining. Flowing from the negative, from the thing, the negatives are going here, losing the electrons to the thing gaining. And then lastly on this, we must have a salt bridge. The function is to maintain electrical neutrality. Follow the negative. The negative ion just keeps going in the same circle as the electrons. Then the positive goes the other way. All right? Now, standard conditions is 1 molar. We'll talk in a second about what happens at non-standard conditions. Let's look at a practice problem. This is from year 2014. Okay? Make it a little bit smaller. Okay? So we have this diagram. A student is given a galvanic cell. That just means battery. That's a galvanic cell. Remember, it's a battery or a galvanic cell is the same name. Represented above, that has a copper and a tin electrode. As current flows through the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. What is that telling me? Okay, so let's talk in chemistry terms. Copper is being reduced, tin is being oxidized. The copper is which electrode? The cathode. So I know because of this, I know that, okay, so I have Cu2 plus in here, I have the nitrates floating around in here, I have SN2 plus, and I know it's 2 plus because of that 2, plus 2, right? And I have my nitrates floating around in here. So what's happening here? It's saying that the copper electrode is gaining, which means it's Cu2 plus going to Cu. Here, this is decreasing. So this is the reduction half. This is the oxidation half. Oops, let me be consistent with my labeling. Okay? Identify the electrode at which oxidation is occurring. Okay? It's the tin electrode, or you just, even on here, you can just draw the oxidation is occurring here. Okay? The tin electrode, you could just say for your answer, the SN electrode is where oxidation. Okay? Explain your reasoning based on the student's observations. Okay? What's the reasoning? Since, okay, but we need to go farther than that. Since it's losing mass, that indicates what? The tin is being oxidized. I would use the word oxidized because that's the anode. What is it saying oxidation is occurring? Okay, because tin is losing electrons going to SN2 plus in solution. Okay, causing the mass of the electrode to decrease. As the mass of the tin electrode decreases, where does the mass go? No, the mass is not going to the copper. Going into the solution. The tin, this mass is going into the solution as it dissolves. Do electrons affect the mass? The fact that it lost 2 electrons? No. Remember, electrons are so light. So the mass, the tin's just going into the solution. The copper is gaining mass from the solution. Okay? Now, technically, the overall mass, I understand what you're saying, is the copper is increasing in mass, but the tin is going into the solution. That's where the mass of the tin is going. Okay? So we have all of that. Okay, so we have to just use our context clues there. And then it says here, in the expanded view of the center portion of the salt bridge, shown in the diagram below, draw and label a particle view. Okay? So again, we have the K plus and the NO3 minus. Which way are the things going? All you gotta do is that. Most of the time they'll ask, hey, they'll give you, do what I did, they'll draw it and say what's missing. You know, some piece is missing. What's the salt bridge? What's its function? Okay, it allows ions to flow to maintain electrical neutrality. Solutions always have to be neutral. Okay? Now, just another example of that if I did Ag plus an electron goes to Ag solid, and I put that in with, let's just say, I put it in with zinc, since I already know that one. Plus 2 electrons goes to Zn solid. I know that zinc is this. Somebody look at page 1105, if anybody happens to be turned there. What is the E for silver?
plus 0.799.
Okay, so which one's getting reduced? The silver, correct? So what's my balanced equation? How am I going to write this? Do I start with Ag plus or Ag? Ag plus Zn solid goes to, now the order doesn't matter, but Ag solid plus 2 plus. Okay? Now, are we balanced?
Not yet.
Why not?
The electrons don't add up.
The electrons don't add up. I'm not charged. You can just balance the charge. So I know that I have a plus 2 there, so I have to have a 2 here. Basically, I'm multiplying this equation by 2. Because I have to make electrons gained equal electrons lost.
Is the E multiplied by 2?
The E does not multiply by 2. That's the wonderful thing about it. It's an intrinsic property. You never have to worry about multiplying that. So that makes it super easy to calculate E red minus E ox. You don't have to worry about coefficients or anything. You just have to make sure you balance both charge and atoms. Now, a different way that they ask that particular question . I just feel like I'm running a marathon. I feel like I'm running a sprint, but it's a marathon sprint, and I'm not in shape for that. So, escape. I need to go to this. I need to go to this. Maybe? Where was it? Maybe that. Okay. So here is a question. This question was actually on the test one of the years that I graded out in Salt Lake, and this was highly, highly missed. Now, in this one, it says, a student is given 50 milliliters of sodium carbonate of unknown concentration to determine the concentration of the solution and mix it with excess calcium nitrate, causing a precipitate to form. And so they give you the balanced equation here. Okay? So here's the balanced equation. I wish I could keep it both on there, but we have that. Okay? So if I have excess calcium nitrate, what's going to be in my solution when the reaction is said and done? I'm going to have some calcium nitrate. Now, since it's aqueous, are they going to be together or apart? So I'm going to have calcium ions. I'm going to have nitrate ions. Where's this going to be? On the bottom, precipitated out. And then I'm going to have some sodium nitrate. Is that going to be together or apart? Apart. So I should have sodium ions, nitrate ions from 2 sources, and some calcium ions, right? So what do I have? What's missing? Calcium. So it says draw in. So obviously I need to draw in. How many calciums do I need to draw in? Does it matter? It said excess calcium nitrate.
It needs the same number. It needs 2. No, yeah.
Half the amount of
Okay, let's make this simple. What has to equal? Charges. Plus 1, plus 2. 1, 2, 3, 4 minus. So I only need 1 calcium, 2 plus. You only need to add in 1 calcium, 2 plus. Okay? Highly missed. People put, because they said there's excess calcium nitrate, they just threw in a whole ton of calciums. Because it's excess. But the charge always has to be balanced in a solution. So this really isn't an electrochemistry, but it's all talking about the charge of a solution in ions. So you only put in 1 calcium, 2 plus. Now if you put in 2 calciums, you just have to add in the 2 nitrates that went with it. But notice, sodium nitrate, there's 1 sodium nitrate, there's 2 sodium nitrate products. I have the 2 nitrates for my excess with 1 calcium, right? Because in my equation, it's 2 nitrates for every 1 calcium. So I only needed the 1 calcium down here to neutralize the 2 nitrates. The charges always have to be equal. Always needs to be neutral in a solution. All right? Okay. I think we're doing well. Trying to think if there's anything else. Okay, that's just a good stoichiometry practice problem. So all those off. All right, so. Think. Oh, I don't like that. That paste one. That was a weird one.
We need like Jeopardy music.
Yeah. Oh, I don't like that one either. They kept asking crazy stuff. I just want a real basic one. Okay. This one is a little bit tougher. Okay? A student hypothesized that bromine will react with metal M more vigorously than iodine because bromine is a liquid at room temperature. So explain why iodine is solid room temperature whereas bromine is a liquid. Why would iodine be a solid, bromine be a liquid? They're both what type of substance? Covalent, molecular, okay, because they're not one of our 5 covalent networks, okay? Are they polar or nonpolar? Very nonpolar, so what's the only type of IMF? LDFs, and with what do LDFs vary? The size of the electron cloud, or just the size of, the size of the electron cloud. So which is bigger, iodine or bromine? So what does that mean about its ion? It's LDFs, stronger. So since iodine is a larger molecule with a larger electron cloud than bromine, iodine is more polarizable than bromine, therefore it has stronger LDFs, making it a solid, whereas bromine is a liquid, requiring more energy to break it or whatever, just saying that. Okay, that has nothing to do, that's just a good review. Okay, which solution should the student add to I2 to reduce it to I minus? So the iodine needs to be reduced. Here's your iodine here. What do we have to look for? How do I tell what I need to add to it to reduce it? The one that's smaller. Because if you put the bigger one in, it's going to get reduced. Okay? So I need the one with the lesser one to get oxidized. So the key is, what should the solution add to iodine to reduce it to I minus? The thing that gets reduced is the more positive E cell. So I need to be something that's going to be oxidized, which is going to be the smaller one. Now, so then it says, so circle your answer below, justify your answer, including a calculations for E for the overall. So it'd be E red minus E ox. Okay, very simple. Okay, what's your explanation on why this one? What's smaller? Don't ever use pronouns. The top one has a smaller E cell, therefore it will be oxidized and the iodine will be reduced. And then you calculate E red minus E ox. So it's going to be 0.54 minus 0.08 equaling 0.46. All right, easy point. Then it says, write the balanced net ionic equation for the reaction between the two. Well, okay, then it says, this is the one I want to say. What chemical do I want to add in? Obviously, it's not this one. But between these two, which one do I want to add in? Okay, let's go A, B, C. How many think it's B? Up in my hands. How many think it's C? How many don't think? If the top one's being oxidized, which direction is the reaction going to go? Left to right or right to left? It's got to go right to left. So what do we need to start with? We need to start with the right and go to the left. We're going to start with S2O3 because it's got to be oxidized to the S406. The oxidation goes right to left. So it's going to be the net ionic equation is going to be, now notice it's 2 and 2, so that's nice. The net ionic equation is going to be I2 plus 2 S2O3s goes to 2I minus plus S406. 2 minus with the charge. The oxidation goes the opposite direction. Okay? Now I don't have a whole lot more time, and there's Princeton Review and all that. You can go and you can do practice problems on this. I don't have a whole lot more time to talk about that. But one last thing on this. Delta G is equal to negative NFE, and that's a kind of a squiggly F. And this is E cell. Okay? This is, oh, that's what I need to do. Yeah, I was forgetting something. Okay, so delta G equals negative NFE. Now, this N is the number of electrons transferred. So what is N going to be even in this one? 2. Okay? N is going to be 2. N's 2 a lot. Okay? F is called the Faraday. It's a constant. It's on your equation sheet. We're going to talk about it more on Monday. It's a measure of charge. What's the charge on a mole of electrons? Is a Faraday. And then E cell is just your E red minus your E ox. Your 110 is your E cell. That's what you would put in there. But the key is this. For a reaction to be thermodynamically favorable, what's the sign of delta G? Negative. Okay? So what must be the sign? It has to be positive. So a positive E cell is thermodynamically favorable. So 3 things as terms of favorability that we've learned. Positive E cell now, negative delta G, and what is the value of K to be product favored? For what must K be to be product favored? Greater than 1. Greater than 1. So the relationship between delta G, E, and K, delta G is negative, E has to be positive, and K has to be greater than 1 for a reaction to be favorable, to be product favored. Okay? Now, this is what I was forgetting. What happens, I got 7 minutes, right? 52?
Yep.
Hey, look, I got it right. Okay, you can stay there.
Okay.
Okay. This degree symbol means standard conditions. 1 molar. What happens if we're not at 1 molar? Everybody turn in your book to page, what page is that right there?
880?
Yeah, 880? 880. And we get the Nernst equation. It's named after a guy. This equation is given on your equation sheet, kind of. Now, if you look on page 880, you will see the equation for the Nernst equation. I'm not quite sure, but it's got R in it. But I'm getting your equation sheet for you. This is the way it's given to you on your equation sheet. E cell is equal, this is the voltage of your cell when it's not at standard conditions. is equal to the cell at standard conditions minus RT-NF times the natural log of Q. Okay? Now, R is 8.31. That's the joules, the 8.31 value for R. T is your temperature in Kelvin, N is moles, and F is Faradays. And a Faraday is a constant. It's 96,500 and 96,400 and, if I have my glasses, 96,485. And we'll talk about that on Monday. Okay? The more significance of that number. Now, if you're at normal conditions, RT over F is going to be that 0.0592. Okay? That's just all that multiplied together. But the whole thing that you need to know here is Q. Because Q is Q, just like equilibrium Q. So, again, if you look then on page 880, okay, and notice that this is on here, they're using common log versus natural log, but it's really not going to matter. But notice we have products over reactants. Now, why do we just have these two things? Because they're aqueous. Solids, liquids, and gases are not in the equilibrium expression, right? So it's still products over reactants, aqueous and gases only. But it's not at equilibrium. That's why we're using Q. If a battery's at equilibrium, what do we call it? If a battery's at equilibrium, we call it dead. Okay? We call it dead. We throw it away.
So humans are just equilibrium after they're...
Yeah, you know, that's why old chemists never die. They just reach equilibrium. All right? We're just dead. That's what happens to a battery. So, here I'm looking. If I'm 1 molar and 1 molar, I'm at standard conditions. 1 molar and 1 molar. What's the log of 1? 0. So this whole term cancels out. So E cell is equal to the same as the normal conditions. But what if I increase the concentration of the copper? I make the copper, the equation's right here, I just make the copper more concentrated. Well, if this number gets bigger than this number, it's less than 1. So what does that mean about the sign of the log or the natural log of a decimal? It's negative. The log of a decimal is negative. You drive me crazy. Let it go. Okay? The log of a decimal is negative. So that makes this whole term negative, correct? So you're going to go minus a minus. So what's that do to my cell? It increases the voltage. So if I have a lot of copper and not a whole lot of zinc, I'm going to have the highest voltage. Reverse that. Now I have a lot of zinc and not a lot of copper. Now this ratio is greater than 1. It's a positive value. So that whole term is going to be positive minus. So that's going to make my battery voltage go down. Now think about this logically. What happens to the voltage of a battery over time? It goes down because it reacts and it becomes product. This goes down, this goes up. So this term right here is what's changing. You're getting more of this, less of that. So the voltage is just going down, down, down until finally there's not enough to make whatever, the wheels of the bus go round and round. So this is called the Nernst equation. You use it, and a lot of times they're just now asking in terms of qualitatively what's going on. Okay? So we can look at this and just plug in. This is given there, but we have to answer it in terms of Q. So the greater the concentration. Now look, if this is 1 molar and 1 molar, the log is 0. What if it's 0.1 and 0.1? Same thing. What's going to be the difference in those two batteries?
amount of electrons in
What,
it?
the voltage is going to be the same, right?
It's just like how big it is.
How big it is. That's the difference between your D, C, AA, and AAA batteries. They're all the exact same stuff on the inside. You just have a whole lot more in the D. So it's got more electrons that can last longer. All right, y'all have a great weekend.